It's my great pleasure to introduce our visitor, Professor Oren. Professor Gao received his bachelor degree in aerospace engineering and master degree in mechanical engineering and geoinformation engineering, all from Technion, Israel Institute of Technology. Professor Gao is currently an assistant professor heading the Swarm and AI lab at the Haifa Department of Marine Technologies. And prior to that, he was the CTO of government office for 20 years, working with research partners across the world and leading research groups. Professor Gao research focus on swarm and AI across scales and delve into complex and rapidly evolving field of swarm and token, leveraging the latest advancements in artificial intelligence to push the boundaries for autonomous systems across scales. Welcome. Thank you so much for coming, and hope you enjoy the talk.
Thank you. So thank you. First, I would like to thank you, Professor Braverman, for inviting me and giving this talk. It's a great honor for me. So, as you mentioned, I come from the University of Haifa, the Haifa Department of Marine Technology, and today we talk about swarm and the robotic swarm different aspects. So, for the general idea, usually we have problems where humans are very limited, such as disaster areas, and we would like to operate different kind of platforms, such as an unmanned swarms. But the problem is that these kinds of platforms, for instance, the swarm, the drones, are very limited. We need to control about each one of them separately, and we might have some cooperations between them in order to have them more efficient during the mission. But one of the biggest questions is how we do that? How can we make many entities work as one? So as we all know, we need them to have some behavior rules. We need them to communicate somehow, and they have to be very resilient by the way they're working. But how can we make that happen? So know that if we wait enough time, this answer will come immediately, as we well know, these guys, the ants, that knows how to do that by themselves and know how to talk to each other, to have some behavior rules, and they're very, very resilient. But that's not only in this case, we also know schools of fish that works together as swarms and a flock of birds that do this beautiful dance. But we would like also to ask ourselves how can they do that? How all these entities can work as one? So we can just take one bird and ask her, but we know that this is not really something we can do. So we understand, for instance, the birds, they got some behavior rules that they're having. They're working together, they got the vision, the collision avoidance, and the group behavior. And by that, they're capable of working as one entity. So what we're doing in my lab, so we are developing different kind of behavior rules using mathematical modeling and AI methods in order to be able to take many entities to work as one in a very efficient way. So my group is there today with 4 postdocs and other masters and PhD students, and we are collaborating with many partners around the world and in Israel, we are very honored to work also with the group of Professor Braverman here in Johns Hopkins. So I will move into different kind of problems now for robotic swarms, and I'll show you part of our works today in this kind of algorithms that we are developing. So one of them is the ocean monitoring for sustainability. And we know that also for this mission, we have very long missions, and we would like to be able to locate and track oil spill around the ocean, and to be very, very efficient with unmanned platforms to face with that. So we developed by using simulators of based on RL framework, the dynamics and the limited communication between agents, because we would like to be able to cover as much area as we want to. So we are putting as part of the reward and the cost function of the system a communication channel and the limitations of the communication channel. And we are looking about that to see how we can monitor. And as you can see, we build different kind of platforms. And you can see the simulations that we use in the MOOS environment, which is a kind of a ROS environment for maritime unmanned platforms developed at MIT. And we even started to have some sea trials showing these kind of platforms working together as a swarm in order to be able to do the ocean monitoring and to be able to work as a swarm for this mission. But we also looked at that when we got an oil spill. You know, the oil spill is not very easy to face with, changing over time, and we need to predict where it's gonna be, and how we can take all these swarm platforms that will be located around the oil spill in the ocean and be able to locate and track it. So we use the LTC networks, which is time-dependent networks, and based on satellite imagery, to be able to build a prediction with the validation for that based on the data that is already available from the satellite images and for the previous oil spill that already happened. And we developed these LTC networks that we will be able to predict the oil spill. And after that, we are just operating in a swarm of unmanned surface vehicles around this oil spill and be able to follow the swarm and then face this kind of oil spill. So as you can see, this kind of this side, you can see the satellite data for oil spill that reported 14 years ago, 15 years ago, and you can see that during time, and that's how it looks like. But in the beginning, you don't see not all of that. And what you see here in the middle, it's the LTC outputs from our model showing the deepwater horizon during time, being able to validate exactly what you can see in the area where the oil spill just happened. We are just using in here a very, very thin model of the data itself, and we can show that just you can see here in the simulation how during time the oil spill is just changing and being located in different area as from the satellite data, and we just developed the LTC model showing that as based on this data. So at the end, you're getting the same contour of the satellite that you can see in here from our LTC model. So we took that and we just that this is a different kind of oil spill around the ocean, and you can see that we are using in here the MOOS environment. And what you see in here is the behavior of the swarm. It's a real-time simulation that runs. It's a real-time software that already can be implemented into the vehicle. The MOOS environment allows you to put that already in the vehicles, so we can see how the contour of the swarm itself using the LTC prediction of the oil spill just is able to monitor autonomously and locate the boundaries of the spill and bound it over time.
Hello, can I ask a question?
Yes, please.
Oh yeah. So thanks. How is this model like learning based or like not learning based?
Yes, it's time variant based. It's just taking the something like the LSTM models that we are familiar with, but we are able to choose a very limited data instead of the very heavy LSTM models. So we can run this kind of the LTC model on a very edge computing capability, which is very, very limited, which is something that is very common for, let's say, surface vehicle in the maritime environment, so we would like to be, as the missions will be as long as we can for the duration. So we would like to have a very limited computation on the edge. So that's what the LTC networks allow us to do instead of using LSTM models.
All right, thank you.
Thank you. So in the next part, I will talk now about the other.
One question.
Yeah,
So, do you fix the model as you see what's going on? Do you have an you refine the model as you go based on what you see?
Yes, based on what we see.
So it's not something you can pre-compute and then it's just communication, or you can really adapt it based on what you see.
Yeah, we need to adapt it based on what we see. It's a prediction based.
So
on
basically, it's iterative to
Yes.
some degree,
Yes,
right?
it's kind of a generative one. It's based on the data that you are measuring now. You're doing a
Okay.
prediction to the oil spill, and then you are updating the swarm behavior currently in order to be able to face the contour and the time variation of the spill.
Okay. So this speed, you use it as a research, like for what really happened there, because you didn't have this technology in 2010.
No, you're only taking the data
For what you
for what we already know that happened.
okay,
We are doing a prediction based on our model, and we can see
right,
the
okay.
validation between what really happened and what our model is predicting.
Oh, I see, because you know what happened at every time.
Yeah, exactly.
I see.
So that's how
Slice
we know that our model is
is
validated.
working well.
So here we're going to talk about other problems that we're working on, which is more related to micro-robotic swarm. We're more working on biomedical applications for micro-robotic swarm. But the problem usually is that we are working in a dynamic flow, and we have a very small, I would say, particles that need to face a dynamic flow. So we would like to develop some behaviors and policies for that. And we are doing that by reinforcement learning method with my PhD student, Joseph Bellman, on the board. So we can see in here that if you're looking on our blood, so we can see that there is it's not a steady state flow. I mean, it's a dynamic flow. It's changed over time, as we can see, and we need to have policies for our multi-agent or swarm, which is very small and very limited capabilities to face this kind of dynamic flow over time, which is usually what happens when we try to work with micro-robots in biomedical applications. So what we did is we created simulations using this package, and we put the swarm, as we can see here. You can see that, and you can see that here the velocity, the x and y, and the pressure that it feels based on the assuming that the flow profile is a trapezoidal wave like this, and over time we are training this based on we're getting a reward for the capability of the swarm to move forward, and we are punishing it if it goes backward, and you can see over time that we are trying to understand what will be the policies that that we will generate for this swarm to move against this dynamic flow in order to get to the other side. I mean, we need to go against the dynamic flow. So it's very interesting to see what happens over time. So we integrated in here a very it's more complicated than what it sees, because we are running CFD simulations in the mini batch all the time, and these outputs of the CFD is getting into the simulations for the policies and for the rewards. and putting out a set of actions that we can get. But this is the flow of simulations that you see in here. It also includes a CFD simulations, which runs all the time in this simulation. It's not only high-level state control simulation. It also puts into it the CFD simulations of these particles inside of the dynamic flow. So what we see that.
But what are we trying to do? What are you trying to optimize?
I'm trying to optimize what will be the policies that will take this swarm to move inside this dynamic flow blood vessel to be, let's say, from start to goal. So where we're assuming, as you can see here, that there are some that the forces that the particles can move is quite equivalent to the dynamic force that this blood as dynamic flows operate on the particles themselves. So there is forces in here, as you can see. There is a pressure gradient and some internal force to each one of them, and also a contact force between them, and a drag that operate on each one of them. So this is a kind of Navier-Stokes formulation for the CFD problem that we are operating. So we are putting all these the gradients and all these forces as part of the dynamic capabilities of each particle to move inside these bodies.
But what I'm trying to understand before, in the problem you showed before, there is a feedback loop, right?
Right.
You do the model, and then you make commands to your drones where they're flying. And then you see what happens and it goes in an iterative way. So we know what is good. You want to track the boundaries, right? But here, what can you do? What is the actions that you can take and what is the goal? What are the actions and what is the goal? How do you know that you do well? Or what is the goal that you want to do well in?
Okay, so I wanted to move against the dynamic flow.
Against the dynamic flow.
Yeah, but I'm not sure how they should do that. I don't have
see.
a solution, okay, for that. So, but
So you want the AI to learn by
Yes.
itself.
yeah, I want the policies to get out from the reinforcement learning.
And what is the assumptions that those micro robots
Okay, so this
actions can do,
Okay,
right?
so this is the assumptions. I mean, that's what they can operate a force. They got a contact between them, okay, and then a drag that operate on them, and a pressure from the dynamic forces itself, and all of that. It takes us. Okay, so we ran multi-agent PPO algorithms for that, and as you can see, we define the rewards as follows. So if you're moving left, you're getting
I see.
you're getting 1 point, but
I
if you are reaching the destination, you're getting many points. And if you're moving forward, and also we know that it is a failure for the simulation CFD itself. So sometimes it crashes, or sometimes the agent decided not to move because the equivalent situation is the best one for them. So they're not moving. So we are punishing them for not moving now. So putting all of that together, we can see, so this is the output for the simulation that we already run. So we see that what they are doing, it's kind of very sophisticated. So part of them are moving to the boundaries, as we can see in here. Okay, they're just moving their behavior to the boundaries and move all to the boundaries where it will be the most
Efficient way for them to move.
But
Yes.
but we can see that over time, part of them are just being shielding on the other ones. Okay, they're creating something that we know, I would say, very similar to what we see with birds, moving as a group, when part of them are taking the size of the group in order to protect the others and reduce the drag. So we see a very similar behavior in here. So this policy generated out from the reinforcement learning is not something that we created. I mean, it's not something that we defined. It's the output that comes from the learning process in this work. So this is that's very interesting. This is a kind of middle work that we are doing in this. So in the next phase, what we would like to do is to try to play and change the input wave. We now use some periodic trapezoid wave. So now we would like to play with it and change it and see how the policy will change according to that. And to add some behavior rules that we did not implement it yet. That to push the nearest neighbor to agent to you, so maybe that can change, and creating some such kind of magnetic forces between the agents, and see how is that going to change the policies that will be generated from the reinforcement learning framework that we developed. Okay, so I'm now
in things like that. My experience is you really need to be very careful how you set the reward.
Yes.
Yeah, because there can be unintended consequences here. Because the AI can find, it will really optimize your reward. So if your reward is not precisely stated, it will find a way that will be counterintuitive.
Okay, so now I'll show you other work that we are doing. Which is our, I think, very ambitious research to try to do some prediction of CFD or computational fluid dynamics analysis by using a machine learning and to generate maneuver of AUV, which is autonomous underwater vehicle, for this kind of problem. So let's say that we would like to generate a trajectory for an autonomous underwater vehicle. And we would like to do that just, from point A to point B by using some obstacle avoidance with dynamic modeling. That's good. But what we would like to do here is to predict the CFD capabilities of these platforms in the underwater environment and to see how we can generate better trajectory based on what we think that CFD simulation outputs will be. Okay. Okay, it's a bit tricky one because usually we are doing CFD simulations to see what will be the forces. What we're doing in here is trying to predict what will be the CFD, by that understanding what will be the forces, and then to change the maneuver of the platform from this output. Okay, so we're doing the opposite way on to work with that. This is my work, my students Oren, and so let's say a few words about basic hydrodynamics. So we got the AUV. The AUV is an autonomous underwater vehicle. It's underwater platform, very non-constrained of the vehicle. And usually we are using CFD, which stands for computational fluid dynamics, which is a numerical method to simulate interaction between the body and the fluid, which help us to predict the forces, the moments, and the flow behavior. And that's a very extensive and very long time computation simulation. It's not something that you can do in an hour or two. Usually it takes weeks or months to get a very good CFD output. So what we did is just taking all these assumptions. We ran many hundreds, thousands of simulations of CFD for scenarios that we know, and then we created a prediction for this AI methods to predict this kind of CFD simulation. And we're also doing a validation in C trials for these capabilities. Okay, so when we would like to be able to say that our model is it's reliable for maneuverability of AUV in complex environment, we need to be able to capture the interaction between the vehicle and the flow, which is not a simple task, and to predict in real time the forces and the moments, the moment and the responses on the vehicle itself. So that's a very complicated task. For that, we're also using a framework of reinforcement learning that will help us to put all of that together. So our approach is to learn the hydrodynamic response from CFD simulations. And that is something that we'll put, as I mentioned in the beginning, into the online phase of the trajectory planning in the RL framework. Okay, so we created a whole bunch of work that helps us to do the predicting the physics-informed prediction of the hydrodynamic response of the vehicle. We trained CFD data, and we estimated by that we estimated the forces, the moments, and the flow characterization of the platform itself. And then by that we are correcting the motion and the control efforts of the vehicle. And we're putting all of that into the execution of the maneuver for the platform. So we had to validate the first stage, being able to say that we are really predicting CFD model, that we got validation for that. It's not a simple task because there are a lot of variation of the initial conditions of the simulation. And it's very complicated task, but we ran thousands of CFD simulations on our specific platform that we are working in. We built a model, we tested it, and compared that with many evaluation criteria, and just to make sure that we got validation for that. And with that, one of the main features that controls on this behavior of the prediction of the CFD, and we got a very good validation for that without confusing. And we are now also doing C trials with the same platform.
So how do you know the error? How do you know what the error was?
Oh, so we got the complete CFD simulation, which is a ground truth.
Okay, so you looked at as the ground
Yeah,
truth.
that's the ground truth. But what we're gonna do is to make sure that we would like to know what will be the difference in C trials between this ground truth that we got in CFD and between the real coefficient that we're gonna measure in C trials. Okay, so this is the ground truth to predict the same output for the CFD simulation. Okay. So let's say we got an error, I don't know, for 2%.
No, but the simulation is your ground.
Yeah, it is. But we're also interested to know how our simulation is good related to reality, which is our question, but it's also very interesting.
Okay, so do you have a real life thing you measure?
Yeah, we're gonna measure these forces on the platform itself.
In real life?
In real life.
Okay, why is that not be the ground truth?
Oh, because we cannot make thousands of experiments, but we can run thousands of CFD simulations. Okay, and that's the difference. I mean, if we're gonna
Okay.
do C trials, we're gonna have.
I'm just trying to understand what you're doing. So what you're saying, I'm gonna validate the simulation
Yes.
by doing very limited experiment in real life.
Yeah.
And then I will treat the simulation as the ground truth if I manage to validate.
Right.
That's your approach.
Yes,
Okay.
that's approach. Yes. Yes. Because I have to know what is the difference, what is the sim to real here, what is the gap. I must know that. Otherwise, I'm gonna trust my simulation, but I don't know what is the error. So I must have this understanding, but still the ground truth will be the simulations.
After it's being validated.
As it's been validated, yes. But So what we
So what are you trying to do? Save on the computation?
yes. I'm gonna say
Okay,
what
so you want to use the AI
I'm gonna, yeah.
to not do
Not
the whole
just-
computation.
I'm gonna do a CFD
I
computation.
see,
I'm gonna do only a prediction.
I see. So in that, you will be both able to do almost as well as the simulation
Right.
with paying fraction of the cost.
Right.
So that is your goal.
Yeah, that's my goal, but based on that, based on these outputs, okay, I'm gonna plan my maneuvers for the AUVs, okay, in real time.
I see,
Which is
which you
something-
cannot do in
You
this,
cannot do
okay,
this,
that's
okay?
the issue, okay.
That's the.
You wanna
the
take
old
it to
way.
real time.
Yeah, I wanna
Okay,
do it in
now-
real, it's kind of doing CFD in real for maneuverability.
And are
Something-
you're able to do that? Like
Yes.
you are able to be,
Yeah,
basically what you're doing is you're approximating
yes,
with fraction of the cost, you can make it real time.
right,
And it kind of like you're approximating it nice, relatively close.
but then you can say, okay, I can change the maneuvers. So
I
we
see.
can be a lot more efficient in our maneuverability by that. Which is something that's still not done, even though it's not very, I mean, you can think of that, right? I mean, but you can see in here how the simulated AUV trajectories is being changed based on our prediction of the CFD performances. So we would like to put all of that into RL framework. So the maneuvers will also include all the dynamic, I would say CFD brain into it, which is something that you cannot do today. So that will give us a lot more efficient and a lot more energy, I would say, efficient trajectories or time optimal trajectories into this kind of RL framework if we can define the reward according to that. Okay. So that's a very interesting one. So yes, so what we are now doing is putting all of that into the RL framework and also include all of that as part of the trajectories that we generate. Okay, so the last thing I want to show you is it's not related to Swarm, but it's still a very interesting project that we're working on. We call it sonar to image. So we're now training a diffusion model, taking a lot of sonar data, which is correlated to image data. We got this kind of data set, and we are training this model. So we would like to, after that, taking only the sonar data, sonar image, and to generate from that image, camera imaging. So that's very interesting work. You can see here how it we got our results for now. We can see that this is the real sonar image, okay, and this is the correlated camera image that we took on the same sonar image, this camera image, and that's what we constructed based on our sonar data only from our model, using our diffusion model that we developed, which is what we would like to do in the future, that you will give me sonar image and I will give you camera image based on only for this sonar image as you've been there and took camera image. So that's a very interesting research. We believe that that can also change a lot of the way that that this work is this world is working today. Our capability to move from domains of sonar to camera imaging in underwater environment, which is very interesting work. And that's been done by my student Yitzhak Fabian. Very high-end work. So I hope that was interesting. I'm trying to go part of our work today for swarms. Of course, fields from ocean monitoring to what we are doing in biomedical with micro-robots, Locomotion, dynamic flow, over CFD maneuverability approximation for AUVs, and just show you a bit of what we are doing with the fusion model. So I would like again to thank you, Professor Braverman, for inviting me, and thank you all for listening. Thank you.
Any questions? Thank you so much. Questions?
Hey, so I can ask a question. So maybe it's like a little bit, not very specific, but you mentioned you want to apply. So you have this like, actor critic thing to network for reinforcement learning for medical applications. But I want to ask like, it has unintended consequences as like people have asked. So have you considered this aspect? Like for instance, reinforcement learning could like fail, and when it fails, like for medical applications, it might be very bad, right? So do you have any comments on that front?
So when we are putting that into our real environment, so we are trying. Yeah, it's very hard to put all of the I would say the variables into this kind of simulation. But from previous work that we know and already been done on the cancer particles research,
Right.
we know that these assumptions of that we do that there is this kind of forces, and the fact that particles and the flow itself are very similar in their forces. These are common and logical assumptions for the problem. We still did not put into it more, I would say, a random process to model the problem.
I see. Yeah. So I want to mention this because also like, VOVA and some of us work also on like more algorithm with, formal guarantees. I think if you incorporate some of those, it might also be helpful for applications like this, because reinforcement learning optimization could be very unstable, right? So that like if you have any type of provable property, then it could also be helpful for something like this, I believe. Yeah.
Thank you. That's very important. Thank you.
Additional questions?
Yeah, can you say a few words about how you validate your simulation in the real life environment, maybe? How is it done?
The AUV problem?
Yeah.
Okay, so what we're
Or
doing.
any one of these. You showed two different.
I think that in AUV case, that's the best way to explain it. We're gonna put, for instance, on the platform itself, specific sensors that measures the pressure and the other environmental conditions, and mostly the salinity, the pressure, the environmental parameters. Based on that, and then of course the velocity, and based on that, we know that we can measure and put out of it the forces that's being operated on the vehicle itself. Okay. So by that, we know that we can and we can compare that to the forces that we generate from the CFD simulation. So by that, we can try to validate.
But you use it in real life, right?
Yeah.
So how do you do it? You have a vehicle?
We have platforms. Yeah, sorry, I didn't mention that. We got several AUVs. We got mothership. We're going out for 6 rounds. We're putting the vehicle in order. We're going to do it in 2 weeks from now. It's a huge experiment. It's a very costly one, but it's very important for us because that helps us to validate our performances and our simulations. And yeah, so that's very interesting work because we are doing that from the simulations to the field. I also showed you here for the ocean monitoring, for the swarm platform, And this is platform that we created by ourselves. And this you can see a real-time, a real live platforms that runs and running the this kind of algorithm of this communication link between them to be able to cover as much area as we can. So we're evaluating all the things in
I thought they will be underwater, right?
Oh, the AUV is underwater.
Oh, but then they cannot communicate, right? How would they communicate
Oh,
underwater?
no, this is almost for surface, okay?
Okay, a surface.
Yeah, this is surface with communication. For the underwater, we are not communicating, as you mentioned, but we are measuring. We have other project of swarm of AUVs, which is underwater vehicles. So then this is a whole other problem. There is no continuous communication, but it's acoustic communication, which is very limited, very narrow communication, but they're being able to send very specific limited messages, but they still can try to work as a swarm. This is the other project that we're now working on with MIT, and we're trying to move it forward. Yeah, very interesting topic.
So is it possible in principle to communicate underwater as a swarm?
It's not what we call communication. It's not kind of RF communication, but it's we need
One-way message.
Yeah, it's a one-way message, and we need to define all the framework of the swarm on very different way, so they will be able to work in this kind of constrained communication.
Any additional questions? Okay, let's thank the speaker again.
Thank you. That's a great talk.
Over. In
Thank
that
you.
last thing, we have a couple of world-class people in your talks.